Hey folks, I'm just going to go over the swinging regime lecture. I wanted to get started on this because I wanted to give you guys as much time in MATLAB as possible. So I'm going to go over how the swinging regime works. The swinging regime happens right after impact. So JAI, just after impact. The falling regime was the just before impact. So falling regime JBI just before impact. So we want to relate somehow what's happening right before the impact to what's happening right after impact. So in order to do this formulation, we're going to have to consider similar methods as the falling regime. So if you look at the picture, these are the three vector loops that you need to solve for the kinematics. These vector loops are also provided to you on Canvas. Loop 1 is pretty straightforward. Loop 2 is also straightforward. Loop 3 is a bit tricky. So I'm going to provide you the equation so that we do not have any consistency issues. Loop 3, due to force transmissibility or vector transmissibility and the parallelogram law, the equation for loop 3 is actually going to be R3 equals R of C relative to A minus R C relative to D plus R E relative to D. So think of a similar approach with these three vector loops is it's going from the impact point, fixed point. So that's going to be your fixed point of rotation. And these vectors are drawn to the center of mass of each link. Okay. So now that we've taken care of that, think of a similar method of solving for the kinematics of this mechanism. Now, if you recall, last week we had talked about a vector called chi. So that vector is called chi, which is the vector that had the three state vector portions. So these were part of the state vector. And then we also had x1, y1, x2, y2, x3, y3. And this is all transposed, right? Because it's a column vector. So, and recall with chi, we can take the derivative, get chi dot, and we can take the derivative to get chi double dot. Recall from last week, so last week we had an equation for the kinematics that was chi double dot is equal to a x double dot plus a. So that is going to be actually pretty similar. So just keep in mind though that this chi double dot is not exactly the same from falling as it is for impact. So chi double dot in the impact or the swinging, sorry, is going to be equal to, we'll call it a B vector, B X. Sorry, let me make these bars over. Plus B. Okay, so you're going to use those three vector loops to find the center of mass equations. Okay. So that is going to be pretty similar to last week's analysis. that these big B and little b are different. Okay. So now we can talk about, so this was all your kinematics. So the next thing we can talk about is kinetics. Now, kinetics is, here's where it gets tricky. I highly recommend that you do one thing before you start this, is to watch Charlie's video on impact analysis. That is what inspired me to also use this methodology. So what we're thinking about in this regime for swinging is, as we've talked about, swinging is what is happening just after impact. And we also have a just before impact condition, which was considered the falling regime. So in the kinetic analysis, we can go and look at these. So I'm sharing what was from Charlie's video. I recommend you also take notes. So you'll see that one equation here, this equation is formulated by analyzing all links. And you'll see that there's the mass times the velocity, so all the linear momentums of the center of masses in the I theta dot, so I omega terms as well. And then you'll also see the resultant force of the ground force at A from impact, as well as the gravity forces, times delta T, which we assume impact delta T approaches zero, and the after condition. So we can come up with a relationship between angular momentum for this condition. So that means we can find out that this approaches zero, right? Because dt is approaches zero. So that means that the angular momentum before impact is equal to the angular momentum after impact for the whole mechanism. These formulations are going to be very important towards forming our kinetics matrices. So definitely watch Charlie's video so that you can get all these notes, because I know I'm going quickly for the sake of time. Link 1 is removed to form equation 2. That means that link 2 and link 3 are the only ones that are analyzed, and as a result, and I did not draw out so you need to draw the MV terms and I omega terms. Right? And remember, theta dot 3 is equal to 0. Or sorry, I3. I3 is equal to 0. Theta dot 3 is not 0, because it's a state variable. So you transfer the reaction force from point A along here to point C, because link 1 is removed. We want to form a system of this angular momentum approach to form 3 equations for the moment and 3 equations for the acceleration, angular acceleration terms. Remember how we said the sum of the moments of the FBD side is equal to the sum of the moments on the KD side? We're going to take a similar approach, as we're going to see soon here. So now, lastly, where link 1 and link 2 are removed, again, I did not draw the appropriate MV terms that are needed for sake of time. But those, you can imagine now, see, remember, we transferred the reaction force up to C, and now we're going to transfer the reaction force over to D. Okay. So, okay, with all that being said, let's go back to our how that helps us in our analysis. How is this going to help us? So that, remember what I just showed you, that was considered regime 2. So in regime 2, as we just went over, HA is equal to HA prime for all lengths, meaning before is equal to after. So that's the angular momentum of the reaction point. And then HC is equal to HC prime. That's links 2 and 3. And HD is equal to HD prime. That's link 3. Okay. So with all that being said, I want to show you guys how an FBD KD is similar to an impulse momentum diagram. So first, let's consider an FBD KD. So consider FBD KD, because the whole point is to do the regime 2 and regime 3 simultaneously. So we're going to have something, we have an arbitrary body and it's being acted by multiple forces. And that's equal to MA. So My double dot, MX double dot, MX double dot, and I theta double dot. So now let's consider a impulse momentum diagram. So that's going to look something like this. So we have the before condition. So that is My dot, Mx dot, I theta dot, plus the, force term, work term. So, or the impulse term, sorry. So that's going to be F. How did I call that? F3 delta T, F1 delta T, and F2 delta T. Okay. And then that's going to equal to the after conditions. So, or just after impact conditions. Now look at this. The FBD, the impulse momentum diagram, is simply the time derivative integrated form, or the time integrated form of the FBD KD, right? So you're looking at these. So, right, because the integral of F dt is called impulse. So the FBD KD, like all that is, and look at, see, that term is how this appears. And then M, the integral of M X double dot, for example, is going to be equal to M dt, right? This is a time integral. So that's going to be equal to M X dot. So with that in mind, we can just make the assumption that summing, or we know that summing moments is procedurally identical for both diagrams. So we can think about the angular momentum as being a linear combination of the angular velocity plus the horizontal velocity plus a constant times the vertical velocity. Using that same linear combinations, we know that, recall that d h dt is equal to d of r cross m a, right? And that is, sorry, this is r cross mv, right? And that is nothing but r cross ma, because the only term that's dependent on it is dv dt. So that is equal to the sum of the moments. So that means that the sum of the moments is nothing but a linear combination of the angular acceleration plus the horizontal acceleration plus the vertical acceleration. Okay. So that means that we can find three separate equations that are related to the angular momentum, because we have these, right? So I'm going to copy these. Paste them here. And something got a little whacked out there, so I'm going to need, never mind. Just, you guys get the idea of the angular momentums? What I'm saying now is that the sum of the moments about A on the FBD side is equal to the sum of the moments A on the KD side. And that's similar to the angular momentum of A's before impact is equal to the angular momentum of A after impact. So you can get, essentially, this is going to be row one of a new vector called G, and row one of the M matrix. Okay. Now let's recall that last week we had a relation from falling regime that little m, is equal to big M times chi double dot. And what did we do for that? We performed some inverse operations and substitutions with chi double dot from kinetics. And we got an equation for x double dot. Ma inverse times little m minus big M times little m, or times a, little a. It's the same process. So G bar is equal to M, and this M matrix is not the same. So this is MJAI, not same as MJBI times chi double dot. Okay. So that means that from inverse operations, our state vector derivatives can be computed as MA, MB inverse times G minus MB. Okay. One other thing is, so yeah, you're gonna want to do this operation. So sum the moments about, now it was, we moved it up to C, yeah. So right, that's gonna be row 2 of G, and that's gonna be row 1 of M. And then the sum of the moments about, I think it was D. So that's row 3 G, and row 3, sorry, typo, row 2 of M. All right. So that's everything you need for the kinetics regime. Your FBDs, your relevant similar FBDs are in the impact notes off of Charlie's video. So I would look at that. But other than that, you need to keep just one last thing in mind. So in MATLAB, we are going to have a script in the term project template, which is called JBI and JBI to JAI, which you're going to be performing a lot of these operations in. So that script, like you perform the like M, you put the A matrices in there, you put the B matrices in there, everything goes in there basically. So M, recall from angular momentum that M chi dot, right, because that is equal to X M chi dot, or sorry, yeah, so this is essentially like the angular momentum, JBI is equal to M chi dot JAI. So that means that M times A X bar dot equals MB X bar dot. So that means that X bar dot is equal to prime. Let's put a prime there. MB inverse MA X dot. X dot is not the same as X dot prime, but pi dot is equal to pi dot prime, since it happens instantaneously. Okay, so this JBI to JAI sort of methodology is going to set up initial conditions for the swinging regime. But in order to get initial conditions for the swinging regime, you need to do the hand calcs for the swinging regime. So we need to do these hand calcs before we can start putting things into code. All right, class, that's all I've got for today. And please reach out with questions. I'm going to give you guys an extension on these calcs. I expect them to get done 2 weeks from now. So we're looking, or wait, this is week 7. So please submit something a week from now. So that's gonna be March 1st. Because we're gonna get into MATLAB next week, and it'd be good to have most of these calcs done if possible. And yeah, let me know if you have any questions. Okay, thanks. See ya.